Welcome to a video lecture on covalent structures, our essential understanding for today. Lewis structures, or electron dot structures, show electron domains. And this is just talking about where are the electrons in bonds or not in bonds in the valence energy levels. And we can use that arrangement of electrons to predict molecular shape. And if I know its shape, I can predict some of its properties. So our specific objectives for today, we're going to review those Lewis dot structures. We're going to predict shapes of molecules using those Lewis dot structures and VSEPR theory. We're going to understand resonance and talk about polarity of molecules. And then we're going to look at some special vocab, allotropes, giant covalent solids or network covalent solids. And then we're going to define coordinate bonding, which is sometimes also called dative bonding. All right, let's get going with a little review of Lewis dot structures. So CO2, remember that we're always going to put the odd guy out in the middle, or the element that's more to the left, and so carbon's going to go in the middle. I'm going to count valence electrons. Carbon has 4. 6 times 2 is 12. Total, I have 16 electrons. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16. Oh no, I ran out of electrons. Whatever will I do? Well, of course, we're going to make some double bonds. So I'm going to take some away and put some in the middle. We're getting closer. How about I take another pair away and I put, oops, I took the wrong ones away. And I put some more in the middle. Good. So now I have my 2, 4, 6, 8, 10, 12, 14, 16 total electrons. And everything has a full octet. Let's do NH3, N in the middle, H around the outside. Nitrogen has 5 valence electrons. Each of those hydrogens has 1. 1 times 3 is 3. Add those up and we get 8 electrons. Of course, we're going to start with 2, 4, 6 between nitrogen and hydrogen. And that last pair is going to go on the nitrogen because hydrogen already is stable at 2. So now everybody has a full octet, or duet, if you will. Water, H2O, oxygen in the middle, hydrogen around the outsides. Hydrogen will never, ever, ever go in the middle. We're going to start with pairs. Ooh, I didn't count. Oxygen has 6, hydrogen has 1. There's 2 of them. All together, that's 8. We're going to start in the middle of our atom. So there's 2, 4, 6, 8. Good? Good. All right. So let's talk about VSEPR theory. So VSEPR stands for valence, shell, electron, pair, repulsion. And that's our VSEPR. And the idea here is that we're looking just at pairs of electrons in the valence energy levels and how they repel each other. And that repulsion is going to let us predict how the atoms will be held together in bonds, like what bond angles they'll have. And you want to memorize these. So yay! But they make a lot of sense, so it's not a terrible memorization thing if we understand the concept. So we're looking for lone pairs of electrons and bonding groups of electrons, and we're always going to focus on the central atom in the molecule. If there are 0 lone pairs on the central atom and 2 bonding groups, so bonding group can be a single bond or a double bond or a triple bond, just groups of bonds. If we've got 0 and 2, then it's linear. If we have 0 lone pairs and 3 bonding groups, it's trigonal planar. And I'm going to talk a lot about those details on these next couple slides. But I just wanted to give you the big overview. Here are some specific details. So focusing on just the idea of 0 lone pairs and 2 bonding groups. So this molecule is basically CO2. Here's our carbon, here's our oxygens. We had those 2 double bonds around carbon, and then oxygens had 2 more pairs of non-bonding electrons. I only care about the electrons on the central atom. Carbon here is our central atom. It has 2 groups of bonds. 1 group, 2 groups. Those groups are both double bonds, but there's only 2 groups of bonds. This molecule is going to be linear because the best way for these atoms to spread out and these electrons to repel each other as much as possible is to basically go in a line. and so our bond angle would be 180 degrees. We're going to call the shape of this guy linear, which makes sense because it looks like a line. In this little group, we're going to look at molecules that have 3 electron domains, either 0 lone pairs and 3 bonding groups, or 1 lone pair and 2 bonding groups, but the idea is a total of 3 electron domains. The geometry, if we're counting the electrons, all of the electrons, bonding and non-bonding, is trigonal planar, and I'll talk about what that means in just a second. So this model is showing us 0 lone pairs and 3 bonding groups. So these bonds could be single, or maybe there's a double, but the idea is that there's 1, 2, 3 bonding groups, 3 bonding groups on the central atom. This is going to lead to this trigonal planar molecule. What's interesting is, what if I have 2 bonding groups and then 1 lone pair of electrons on the central atom? So there are electrons here. What's kind of cool is that these electrons are going to take up space just like these electrons take up space. And so even though there's really only 2 things that are bonded to the central atom, because of these electrons that are repelling those electrons, we're not going to have a linear shape like carbon dioxide. Instead, we're going to have what we call bent. What's kind of crazy, our trigonal planar molecule that has 3 bonding groups is, with this makes sense, it's going to have a bond angle of 120 degrees, because we know that 120 degrees around a circle times 3 is at 360. If I'm looking at this guy, my bent molecule, you're like, well, there's also 1, 2, 3 things. It should be 120, but it's not. And the reason is this. Our lone pairs of electrons, because there's no nucleus over here kind of holding them in place, they actually take up more space than our bonding pairs of electrons. And so they're going to push those bonding pairs of electrons a little closer together, and so it's going to be slightly less than 120 degrees, maybe 118 degrees, but it'll be less. And so lone pairs of electrons on that central atom are going to push those bonding pairs closer to each other, and the bond angle will be less than 120 degrees. Lone pairs of electrons occupy more space than do the bonding pairs. Lone pair, lone pair, lone pair, bonding pair, bonding pair, bonding pair. Bonding pair here, that's going to take up less space. If I'm looking at lone pair, bonding pair, like here, that's going to take up a little bit more space. And then in a couple more slides, we'll look at lone pair, lone pair. Good, good. So planar, because on my next slide, we're going to talk about trigonal pyramidal versus trigonal planar. So remember that in Spanish, plano means flat. I used to live in Plano. It is actually very flat. And so this molecule is going to be flat. So 120 degrees this way, but if I were to look like over the top of it, it's going to be flat, 180 degrees. So we were just looking at that trigonal planar molecule. Now we're going to throw in this weird thing, trigonal pyramidal. Not quite the same. Trigonal pyramidal is based on 4 total groups of either bonding or non-bonding electrons on the central atom. It could be 0 and 4 to make tetrahedral. It could be 1 and 3 makes tetrahedral, or 2 and 2 makes tetrahedral. So we're going to look at 0 and 4 first, because this is the one that makes the most sense. So this is something like carbon tetrahydride or carbon tetrachloride, where I have my central atom carbon, and then there's 1, 2, 3, 4 things bonded to it. It might be tempting to draw like a giant plus sign and say, haha, those all have 90-degree angles. In fact, because molecules are 3-dimensional in shape, we can kind of push them back into the paper computer screen and pull them out toward you from the computer screen. And in 3 dimensions, these actually are going to have angles of 109.5 degrees. 109.5 degrees. And we're going to call this shape tetrahedral, tetra for 4, tetrahedral. So what if one of my molecules has those 1, 2, 3 bonds, but then it has a lone pair of electrons here. So 3 bonding groups and then 1 lone pair. Just like on the previous slide, these guys are going to take up space. And so we're going to go from that idea of trigonal planar, where these 3 guys were spread out fairly evenly at 120 degrees. But now we're going to have these lone pairs of electrons here pushing down on these guys. And so we're going to end up with 1, 2, 3, 4 groups of electrons. That's a 109.5 degree angle. But because these guys take up more space, we're going to push it down a little bit, and it's going to be less than 109.5. What if, like water, I have 2 non-bonding pairs and 2 bonding groups? 2 non-bonding pairs and 2 bonding groups. Same thing. I have a pair here, I have a pair here, I have a pair here, I have a pair here. That's 1, 2, 3, 4 things. That means our electron domain geometry, if I'm counting all the electrons, not just the electrons in bonds, is going to be tetrahedral. I'm going to have my molecule, just where the bonds are, is going to be bent. It's going to be bent. And the reason it's bent instead of linear, we don't have water like this. We have water like Mickey Mouse ears. And the reason is because these electrons and these electrons are pushing those guys in. It's going to be another less than 109.5 degree, but it's actually going to be less than 109. So this guy is maybe like a 107. This guy's like 105, getting really, really small. Because 2 lone pairs are actually going to squish things together even more than just that 1 lone pair next to a bonding pair. All right, so these 3 guys we did previously in the lecture, so I just redrew them here. And then to keep things going fast, I already added the other Lewis dot structures. We're just going to predict shapes right now. So I've got 1, 2 bonding groups, no lone pairs on that central atom. And so this guy is going to be linear for both electron domain geometry and molecular geometry. Linear with bond angles of 180 degrees. Water, H2O, I have 1, 2 bonding groups and 1, 2 non-bonding groups. A total of 1, 2, 3, 4 electron spaces means that our electron domain geometry is going to be tetrahedral. The molecule shape, we're not going to count our non-bonding pairs of electrons, just looking at where we have atoms holding electrons together. And so our molecular shape is going to be bent, not linear, but bent. And the reason is these lone pairs are pushing those guys away from 180 degrees and taking them to about 105 degrees, less than 109.5, which is our number for tetrahedral. NH3, I've got 1, 2, 3 bonding groups and this 1 non-bonding pair. That's 1, 2, 3, 4 things all together, so our electron domain geometry will once again be tetrahedral. But I only have 3 atoms, not 4 atoms, and so our molecular geometry is going to be trigonal pyramidal. Pyramidal and not planar because these guys are pushing those guys down a little bit, and so we're going to have bond angles of less than 109.5. Carbon tetrachloride, 1, 2, 3, 4 bonding groups on the central atom carbon is going to give us an electron domain geometry of tetrahedral, and because there are atoms on each of those groups of electrons, our molecular geometry is also tetrahedral. You might be thinking, but wait, what about all of these non-bonding groups? We don't care. We only care about that central atom. It's the most important when it comes to shapes. SF2, looking at sulfur difluoride. So I've got 1, 2, 3, 4. That means electron domain is tetrahedral. And then I've got 2 non-bonding groups and 2 bonding groups, and so our shape will be bent, a lot like water, less than 109.5. Boron trichloride. You're like, oops, Lentz, you need to make a double bond because boron only has 6, not 8. Nope, crazy thing. Our halogens will never make double bonds, ever, ever, ever. And so chlorine refuses to share anymore. And boron only had 3 to share. It started with a valence of 3, and now it has 6, and that's better. It's not great, like 8, but it's better. And also boron is like one of those weird metalloid things. And so is this really a covalent compound or is it ionic? Interestingly, kind of both. But we're going to go ahead and draw it here like it's covalent. So there are not 8 electrons on the central atom. That's okay. Close enough. Right. So we're going to count 1, 2, 3 bonding groups on that central atom. That's going to make our electron domain geometry trigonal because it's 3. But because I don't have any extra electrons up here, it's going to be planar instead of pyramidal. Because there are atoms on all 3 of those bonding groups, it's going to be molecular geometry, also trigonal planar, bond angles of 120 degrees. Good? Good. All right, so let's do 2 more here. Ozone is O3. This is ozone. It's a pretty cool molecule. It has 3 oxygen atoms. Each oxygen atom has 6 valence electrons times 3 makes 18. And so I'm going to go oxygen, oxygen, oxygen. We're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, we're so close to everybody being happy. So our central oxygen only has 6 electrons. We are going to make a double bond because oxygen will double bond. And I'm going to put it on this side. Or we could have put it on this side. And this idea that I could have a double bond over here or over here is resonance. Resonance happens when I have 2 or more Lewis structures that represent a particular molecule or ion. This ozone molecule can be either this or this. And so the resonance form, I'm showing individual Lewis dot structures that can contribute to the resonance. But what happens in reality, this is so cool. What happens in reality is that these electrons, that extra pair in that double bond that could be here or here, they actually go back and forth. That's amazing. And we call these guys delocalized electrons because they're not stuck in a specific bonding place, but they kind of flop back and forth between those 2 bonding places. And so we can show that either by resonance form, the individual Lewis structures, more than one, that are contributing to the resonance, or we can draw the combination or the hybrid of those forms, and that would look like this. Drawing out my oxygens, and I'm going to add an extra little line here. And that's going to show that I have electrons that are moving back and forth between those 2 guys. Good? Good. What's kind of cool about resonance and hybrid stuff is that it does add some extra special properties to these molecules. Let's talk about the shape of ozone real quick, and then we'll look at SO3, sulfur trioxide. So our central oxygen has 1, 2 bonding groups. This guy counts in those 2 bonding groups. It's not a third. There is, however, this 1 non-bonding pair. So I've got 2 bonding groups and 1 lone pair. That's a total of 3, which means it's trigonal planar. But, whoa, planar. This lone pair of electrons means that our molecular shape, so this was electron domain, our molecular shape is going to be bent with bond angles of less than 120. Good? Good. All right. Let's talk about this other guy. I'm going to make some space. Let's talk about sulfur trioxide. Sulfur has 6 valence electrons and so does oxygen. So sulfur 1 and oxygen 3, that's a total of 4 things that each have 6 valence electrons. That's 24. Sulfur in the middle, oxygen around. We're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're so close. Sulfur is missing 2 electrons. And so I could move this one and put it here. Or I could put the double bond over here. Or I could put the double bond over here. So these are our 3 resonance forms, the 3 individual Lewis dot structures that contribute to resonance. Or I could draw our hybrid form where I've got sulfur and my 3 oxygens, and I have resonance happening around all 3. Because those electrons can move, our delocalized electrons can move around all 3 of those spaces. Delocalization is this idea that electrons are shared by more than 2 atoms in a molecule or an ion, which means that they don't get stuck right here, but instead they can move around. We have delocalized electrons, and delocalized electrons that can move a lot, usually confer some special properties. All right, so we're going to talk about this idea of bond polarity really quickly. And then connect it to molecular polarity. So bond polarity we talked about in our last lecture. We looked at those electronegativity differences between 2 atoms. If there's a greater than 1.8 difference between the 2, then it's an ionic bond. If it's between 0 and 1.8, it's polar covalent. If it's 0, it's purely covalent. But not always is a polar bond going to result in a polar molecule. So molecular polarity is the result of all of the polar bonds contributing to some kind of polarity on the whole molecule. How do we decide if the molecule is polar or not? We're going to do our VSEPR shapes, and then we're going to look to see if we have polar bonds, and then we're going to do some super cool physics vector addition to figure out if there's a net dipole moment. What does that mean? Let's talk. So carbon, oxygen, oxygen. So we do have polar bonds here because carbon and oxygen do not have equal electronegativities. Oxygen is a little bit more electronegative than is carbon, and so the electrons are going to get pulled more toward oxygen than toward carbon. But what's kind of crazy cool right here, these 2 vectors that are showing electrons going this way and this way, they cancel each other out. And so electrons more here, electrons more here. There's not a pole, which would mean a positive side and a negative side, but instead we have negative and negative side. This is not polar. This molecule is non-polar because we have an even distribution of electrons. Boron trifluoride. We're going to have boron and our 3, oh, that was bad drawing, 3 fluorines around the boron. Fluorine is so much more electronegative than is boron. So those electrons are going to get pulled way closer to the fluorine than to the boron. But once again, we have these vectors canceling each other out. They're going to sum up to 0 because once again, we have a symmetrical or even distribution of those electrons. This molecule is also non-polar. NH3. So now I have nitrogen and then our 3 hydrogens. Here you might be thinking, once again, we have symmetrical distribution of our electrons. Look at these guys, how they're all pointed toward nitrogen because nitrogen is more electronegative than is hydrogen. No, because our molecular shape is actually trigonal pyramidal, right? And so those electrons are all pointing up. Plus, we have that lone pair of electrons here, which are definitely pointing up. And so our vector addition, all the directions of all of the electrons moving together, we definitely have more negative things on this side, which leaves these guys to be a little bit positively charged, and H3 is quite polar. CCl4, carbon in the middle, chlorine all around. The shape of this guy is going to be tetrahedral. Vectors, we're definitely going to be more electronegative on the chlorine side. But here, once again, we have a very even distribution. There's a symmetrical distribution of those electrons. And so this molecule is going to be non-polar basically it's going to be negative around the whole entire outside of the molecule. The whole thing is negative, which means that there's no pole, because to have a pole, you have to have some positives and some negatives. Good? Good. All right, little bits of vocabulary now. Allotropes. Allotropes are forms of the same element. We talk a lot about carbons, allotropes, and they're going to have different physical and chemical properties, even though they're the same element. Did you know that carbon is diamond and graphite and the super cool thing called Buckminster fullerene? These guys are all made of just carbon atoms. Only carbon, nothing else. But they have very, very different properties because the carbon atoms are bonded together in different ways. Diamond and graphite are what we call covalent network solids. They have giant three-dimensional lattice structures, a lot like ionic compounds. And so they don't have just a molecular shape. Fullerene has a molecular shape where in this guy, there's like a start and a stop. It is exactly 60 atoms of carbon, no more, no less. These guys can build on each other indefinitely. Diamond can get bigger and bigger. This is a terrible picture of diamond, but pretend like those are all carbon atoms growing bigger and bigger, or we can crack it into smaller pieces. So there's no defined number of atoms of carbon in diamond or graphite. They are lattice structures, kind of like our ionic compounds. They're not ionic, but they're similar in that lattice structure. So let's look at some of these guys. So diamond is a covalent network solid. Sometimes we call it a giant covalent solid. The carbon atoms are bonded tetrahedrally. So each carbon is bonded to 1, 2, 3, 4 other carbons. Each carbon is bonded, well, this is a bad choice. Each carbon is bonded to 1, 2, 3, 4 other carbons if that diamond kept going that way. These guys are crazy hard. They have very high melting and boiling points. I can't even imagine how hot you have to get diamond to get it to melt, right? And it does not conduct electricity. Diamond does not conduct electricity. These bonds are covalent bonds. Electrons are being shared here, but they can continue to be shared indefinitely with more carbon atoms. Graphite is similar but different. So graphite is also a covalent network solid or a giant network solid. We can indefinitely continue to add more carbon atoms, but this time we have carbon atoms bonded to only 3 other carbons. Carbon bonded to only 3 other carbons. Carbon bonded to only 1, 2, 3 other carbons. Carbon has a valence of 4, so that means that one of these guys has to be double bond, but not actually one of those guys is a double bond, but instead we have that resonance where we have delocalized electrons that can kind of jump between one bond to the next. Those delocalized electrons make graphite a really good conductor of electricity. I don't know if you've ever connected pencil lead, which is graphite, not actually lead, to a battery, but it's pretty crazy what happens to the graphite. What's kind of cool about graphite is that it's actually these super cool sheets of carbon that are held together by London forces, London dispersion forces. So there's like a force of attraction, not actual chemical bonds, but forces of attraction that hold these sheets together. And when we use our pencil lead, which is not lead, to write on paper, what we actually do is like just push some of those sheets off when we push on the paper, which is really, really cool. Each one of those sheets, so if I take just one of those sheets of graphite, I now have graphene. So this is just one of those sheets of graphite. What's kind of cool about it, because there's only one sheet, it's actually a 2-dimensional crystal. Amazing! We still have our carbons bonded to 1, 2, 3 other carbons, which means that it is a good conductor of heat and electricity because it's got those delocalized electrons, electrons that can flow from one bond to the next. It is super strong, super flexible, quite transparent, and there's been a lot of talk about using graphene to replace Kevlar to to protect us against bullets. So kind of a super cool thing. We discovered it in 2004, literally by using Scotch tape on graphite to try to get just one little sheet of this stuff, and then it won the Nobel Prize in 2010. All right, so those previous guys, diamond, graphite, graphene, those are all examples of network covalent solids. They can add on more carbon atoms indefinitely. That's different from this guy, Buckminster Fullerene, which was discovered by this guy named Bucky Fuller. And he was able to make what we call buckyballs, because, again, his name was Bucky Fuller. So these are exactly 60 atoms of carbon. It is not an indefinitely growing, can get smaller or bigger kind of thing, but instead it is a molecule of lots of carbon. It is insoluble. It does not conduct electricity because it's a molecule. There isn't like an input and an output for that electron flow to make electricity conducted, but instead it's just a single molecule. It won the Nobel Prize in 1996. What's kind of cool is that we can put things inside these little buckyballs, like drugs or gene carriers, and what's super cool, it is just the right size and shape to fit into the protease active site of the virus HIV and can inhibit that enzyme, preventing HIV from making people sick, which is super cool and amazing. We think, maybe. We're working on it still. We can also shape these guys into tubes, which are interestingly good conductors and could replace silicon in electronics. So if I made it less of a molecule and more of a tube, then those delocalized electrons could conduct electricity. All right, let's look at network covalent solids. More examples. One more example, SiO2. If you see SiO2 pop up somewhere, anywhere, you need to think, haha, this is quartz, this is sand, this is not a molecule. This is not something that looks like this, but instead it's going to look like this. It's another network covalent solid. It is, again, a lattice structure, kind of like an ionic compound, but not. We don't have ions. We do have shared electrons still. It's kind of cool. Each silicon is bonded to 1, 2, 3, 4 oxygens. Each oxygen is bonded to only 2 silicons, but we still have this repeating pattern that could go on indefinitely. That lattice structure makes it have a super high melting point. It does not conduct electricity because there are no delocalized electrons. So this guy's super cool. SiO2. Memorize, memorize, memorize. This guy is a network covalent solid. One last piece of vocabulary and then we are done, my friends. So coordinate covalent bonds, sometimes we call this dative covalent bonds. So this is where one atom is contributing both of the electrons that are shared in the pair. So if I have NH3, I'm going to start with NH3. Nitrogen has 5 valence electrons. Hydrogen each has 1. That's a total of 8. Which gives nitrogen that lone pair of electrons. Those electrons are negatively charged. If along comes a hydrogen ion that has no electrons, it's just a proton, the positive hydrogen is going to be attracted to the negative nitrogen, and it's just going to stick there. And we're going to end up with something that looks like this. And it's going to have an overall positive charge, because we have more protons than we have electrons now. This is the polyatomic ion ammonium. And what's interesting is that these electrons that are being shared between nitrogen and hydrogen, both of them are nitrogens. Hydrogen brought 0 electrons to the bond, and so this is a coordinate covalent bond or a dative covalent bond, because nitrogen contributed both of the electrons that are being shared in this pair. Similar thing happens with hydronium. We're going to have oxygen in the middle, hydrogens all around. It looked like water, and then along comes this extra hydrogen guy, and he's just going to stick. And now I have hydronium that has a positive charge. These electrons were both contributed by oxygen. This hydrogen did not bring any electrons to share. They're sharing 2 that both came from oxygen, and that makes it a dative or coordinate covalent bond. One more, carbon monoxide. I've got carbon, I've got oxygen. Carbon has 4 electrons, oxygen has 6. That's a total of 10. 2, 4, 6, 8, 10. That's not enough. We're going to have to make a double bond. Notice that I'm taking away from oxygen. But wait, I'm going to have to take away from oxygen one more time. And so even though this is 1 carbon, 1 oxygen, carbon brought 1, 2, 3, 4 to the table, oxygen sharing not just 1 pair, but 2 pair to get that triple bond in carbon monoxide. So carbon monoxide also has a coordinate or dative covalent bond. And my friends, we did it! Our essential idea was that we could use those Lewis dot structures to show electron domain geometry and molecular domain geometry to figure out those VSEPR shapes. We looked at Lewis dots, we looked at VSEPR theory, we talked about resonance, those delocalized electrons that can go in more than one bond. We talked about molecular polarity. We're going to talk a lot more about molecular polarity in class. We talked about allotropes, especially those carbon allotropes. We've got the diamond, we've got the fullerene, we've got graphite and graphene. We talked about those giant network covalent solids, diamond and graphite and graphene, and silicon dioxide, quartz, sand. And then we left off with our coordinate or dative bonding, where one thing contributes more electrons in the bond. We did it. Good work.